opportunity to talk to you a bit about the work that we've been doing, basically a bunch of computer scientists led by me and a variety of clinical doctors and researchers across Penn and Mayo. I'm trying to really build not only a platform for helping people do epilepsy research, but in fact to think a bit broader about what would kind of a basic platform for supporting kind of data-centric science look like, not just in terms of the computational pieces, but the broader set of pieces. And incidentally, I think Jeff had said maybe I'm going to completely disagree with all of the aspects there. I think actually maybe we're more in agreement about distribution versus centralization than it might sound like, but I think there are definitely cases where you need a federated approach, and I'll talk a bit about that as we go through the talk. Okay, so many of you probably know more about epilepsy than I do, but just as a bit of an introduction for why we're looking at this problem, worldwide there are about 50 million people with epilepsy, and out of that 50 million, there are actually 20 to 30% of cases that are not treatable by medication. Such people, most of their lives are normal, but they can occasionally end up at some unpredictable and sometimes catastrophic moment actually having a seizure. So my colleague Brian Litt, who is a medical doctor in this area, he cites a case that he knows of where there was a mother who was filling up the bathtub to give her child a bath, and the mother had a seizure and ended up drowning in the bath water as a result of that. So clearly, this can be a pretty major thing. Now, for the cases of people who can't be medicated, the usual practice has been to actually essentially remove part of their skull, implant a bunch of electrodes, and record EEG data for a week-long hospital stay or something like that to try to figure out where it is that the seizures are happening. Basically, you can see spikes in the EEG data when a seizure is happening. And the usual practice there for solving the problem, makes me shudder every time I think about it. Basically, the standard practice is they remove that portion of the brain and, cross their fingers that everything still works okay. I mean, I'm being slightly facetious here, but it really is at that level. Now, fortunately, in recent years, my collaborators and others made a fairly significant breakthrough, which was to actually take a closer look at the EEG data that was coming from these patients, and in particular to sample it at much higher rates than people were typically doing. So I think kind of in the old days, it was sort of at the, we'll sample at a couple hundred hertz. Well, Brian Litt and others were looking at data at 32 kilohertz, right? So we're talking, hundreds of times faster. And it turns out they were able to find precursors in the data about an hour in advance of the seizure. And now there are a variety of companies who are trying to build implantable devices that will watch the electrical activity and actually administer electric currents in order to preempt, in some cases, the seizures. Now, the problem is, of course, we're just at the beginning of all of that. The predictor algorithms are not perfect. We still don't really know how seizures work. In fact, it's not even completely obvious in many cases how to diagnose epilepsy versus sort of normal brain activity. So it's pretty clear we're just at the beginnings of understanding this. And the hope is if we actually start to look at the data a lot more closely with a lot more eyeballs and a lot more computational resources, maybe we can actually figure out what epilepsy is, how it spreads, what's normal brain activity, what's abnormal, the various patterns and features, etc. Okay, so what we set out to do was, figure out a way to make high-resolution data, which is currently available to maybe half a dozen labs across the world, much more broadly available to the entire community. Okay, so really it's about connecting data to scientists and to analysis tools and to algorithms developers and so on to try to really make this study a lot more feasible. Okay, now, when Brian came to me, he said, you're a database guy, we need to build a database for EEG data, we'll put it on the web, and, life will be good. But I think that's a bit of a not to disparage Brian, but that was a bit of a naive view of the world, because just putting the data up on the web is not really enough to make it broadly accessible for science. Okay, so one problem that we identified almost immediately, a typical patient with 100 EEG channels for 2 weeks at a time at 32 kilohertz, you end up with multiple terabytes of data. Okay, and that's not a big deal within a cluster, but it's kind of a big deal if you're imagining you're hosting a web server in Philadelphia and somebody's trying to download it in Australia. Okay, just downloading that amount of data, which is kind of the standard practice in this community, you know, basically people download the data, they run their tools locally, and then they produce their results. That's just simply not feasible at this scale of data. Okay. A second problem, and I think this actually is something that Jeff alluded to a moment ago, there's all sorts of different kinds of data out there, some of which is more structured, some of which is less structured, some of which has a lot of semantics in it, some of which we're not so sure. So, you know, there's image data like MRI or CT, there's EEG time series data, some of this is annotated, some of it is not. EEG data, there are, I don't know, a dozen different manufacturer vendor formats. The different groups who have this data have different metadata repositories. Somehow we need to put that all together. Okay. And then there's another point that I'm going to come back to probably several times throughout the talk, which is it's very easy to say we're going to build a portal for this one very narrow user community. By the time you finish building it, you've probably had the community broaden or move beyond you, and you want to be very careful not to sort of silo yourself into a very static sort of target audience when in fact, you know, especially research tends to expand and cross areas that, you know, formerly were isolated and so on. So you need to figure out not only how to incorporate all the existing data, but also to have a strategy that allows you to broaden. Okay, and another very closely related thing, the analysis tools that people currently use, we would like to somehow be able to make those available as well. Let's not ask everyone to re-implement every single algorithm on their own local machine. Okay, so we'd like to support the array of tools that already exist. Unfortunately, those are in a whole plethora of languages, including probably my least favorite, MATLAB. So MATLAB, Java, C, Python, Perl, you know, every which thing, many of them standardized to different operating systems, and surprisingly, very little done even to compare the success rates of different algorithms. Okay, so not only would we like to bring together all the tools, we'd actually like to start bringing some science to this and saying tool A is better than tool B, okay, or tool C has a bug in it. Okay, so all of those things end up being highly desirable. We would also like to think about fostering sharing. So it's not just about data, it's also about communication, it's about discussion, it's about collaboration, and it's about reproducibility. Okay, if people are running tools over the data and generating results, we'd like to know how that result came to be. Okay, so our goal then was to try to think about, you know, in a systematic way, building upon the experience of our epilepsy researchers and our computer science researchers. Can we design a forward-looking, extensible, really ecosystem for doing seizure prediction research? Okay, so we had to start, of course, with, you know, what are the needs for the user community that we're targeting here, right? And in general, you know, they're fairly simple, right? The first thing is they want to be able to find data, right? We need a place where they can search for the data based on patient characteristics, based on keywords, based on whatever. In general, many of our users, though not all, won't just take the data. They also want to kind of eyeball it, identify interesting regions, and kind of drill down to something that they actually want to look more deeply at. Then they want to apply tools to that data. And the tools might be, you know, downloaded directly from our site or run on our site, or they might be some proprietary tool that just this lab has developed that they're not willing to share elsewhere. Okay, so we'd like to support all of those models of interaction. Anything that they produce, we would like them to store not on their local hard drive, but actually on our site so that it could be documented and archived. Okay, we want to give them the ability to view and edit whatever they've got, and we want them to be able to compare against sort of normative annotations, gold standards, known results, and also the results from previous tools. Okay. And finally, we want to have a platform where not only can they produce these results, but they could actually, for instance, publish papers with stable pointers back to the data. And we want to maintain for each data item its provenance, the description of exactly how it was produced using what tools over what regions of the data, which will make it much easier to reproduce in the future. Okay? Now, beyond that, and this is where sort of those of us who do data integration kind of chimed in, we want to be very careful to think much more broadly than just our current EEG seizure prediction community. Okay? Many of the past bioinformatics data portals that I'm familiar with, the approach was, we're going to find some user community, we'll design a data warehouse and a static schema for that, fix the data types, build up a web infrastructure, develop a bunch of translators to get all the data into this data warehouse, and also fix a bunch of query forms. And basically, at this point, we now have the central sharing point for some particular community. Okay. Almost always what happened was, you ended up with 5 of these communities, not just one, because they kind of all sprung up from different groups. And at some point, you wanted to be able to bridge those communities. Okay. Many of these existing efforts did not scale very well to those problems, right? In general, the moment they needed to bridge out somewhere else, either somebody needed to hand create cross-linking identifiers across the databases, or they had to figure out how to redesign the platform, and that was typically very, very painful. So our goal was, let's not head down that path. Let's aim for something that's extensible in the future. Okay? So here are the key things that we sought to exploit that are sort of relatively new capabilities in a combination of industry resources that you have available at this point today and new research tools. Okay, so one of the big things was, the sort of software as a service model. The fact that, today a modern browser supports all the kinds of interactive graphical user interface widgets that Windows or Mac OS does, that it supports visualizations through HTML5 Canvas and through WebGL, and that in general it supports things that are very, very responsive. Okay. One of the things this allows us to do is say, you don't need to install anything, and if we're going to change the software, it's going to instantly be changed, right? So this means, much like Google, who's probably tweaking all of their services every single day and we don't even notice, right? We have the ability to rapidly update. The second thing, and this was probably the buzzword that got people most interested in our project, the cloud now, the commercial cloud is now a very viable platform for doing, academic and other kinds of research. The cloud has really 2, we think, extremely important properties that have to do with scaling as you need and extensibility. So one of them is, we can start off small, lease storage for as much data as we have, and as we need more, we just buy more. Okay, we don't need to actually invest in the infrastructure for this project. Okay. Additionally, if we want to do very computationally expensive tasks, we can lease compute cycles across the cluster. Okay. In some cases, maybe MATLAB doesn't naturally extend to supporting cluster computation. People may need to re-implement in Hadoop or some other platform. But we have all of these resources at our disposal, and we can work with domain scientists to recode their algorithms as necessary. And, if the upside is they have suddenly a 100 times speed up, something that went from taking a day to being almost interactive, this can actually make a huge difference. Okay? And the other thing that we're hoping to exploit is that all of the major cloud providers have a way of executing code on protected virtual machines, which means that we can also support extensibility where people upload their code to our platform, and if we get the interfaces right, we can execute it safely. Even if it's malicious code, it can't bring down our service. Okay? So this is actually really important if you want to be able to support arbitrary code from arbitrary people. Okay. The other thing, and this is coming from the research side, is there have been a lot of developments in sort of techniques that allow us to incrementally connect new kinds of data and create new kinds of queries. So, for instance, out of my own group, we have a research platform called Orchestra, which is designed to allow us to take a variety of different databases, perhaps hosted in a variety of different places, and interconnect them with a bunch of translators. And the system will automatically sort of synchronize what's in the different databases, propagating changes, translating information, resolving conflicts, and encoding data provenance. So this is, in some sense, the way that we ultimately envision bridging out to, from sort of the public seizure prediction data to possibly private clouds with clinical data in an individual institution, or to other communities in neuroscience or beyond. Okay? And I had mentioned the traditional approach for queries on mini sites is, they predefine 5 or 6 forms, and that's sort of all you can ask. Okay? Clearly, that's not what you want if you're sort of always asking out-of-the-box questions. So we're going to be implementing in our next release support for keyword search across all the structured data, which will allow people to create essentially arbitrary queries as they're going. Any idea why we're getting feedback? Okay. As far as I know, I don't have a microphone. But okay. So just to give a picture. Maybe that's what it is. Okay. So just to give a picture of our basic platform, here's what we have today. We have a server-hosted portal for accessing all of the EEG data that we've gotten from the Mayo Clinic and from Penn. That server is basically sitting in front of cloud-based storage that includes a bunch of images and a bunch of EEG data in a proprietary Mayo Clinic binary format called MEF. In addition, we've built a database for the metadata, for instance, the patient case histories and demographics and so on, and also to encode provenance and annotations and a variety of other information. Okay. So note, we didn't try to stick everything into Oracle. There are certain things like time series data that make much more sense on a cloud storage system, whether it's Elastic Block Store or HDFS or whatever, and some things that make more sense if they're very, very regular, being in a SQL database. Okay. Now, on the client side, we have sort of 2 main consumers of the data. So on one side, we have a web browser interface, and I'll show some more detailed screenshots in a moment. The web browser has sort of taken over the role of the client for accessing everything. From the browser, you can manage experiments, you can view the data, you can search for data, etc. This is all using a variety of web technologies. And the other thing is we have a number of users who basically are locked into this model that they want to write MATLAB code over this data, and they don't want the MATLAB code to be anywhere except on their own local machine. Okay? So we have a variety of web service interfaces where at least, rather than downloading all the data ahead of time and then processing it, they can write code which asks for just the regions that they need at the level of detail that they need. Okay, so basically, if they only need the data sampled at 100 hertz, let's not send it to them at 32 kilohertz. Let's downsample it and send only the small bit. Okay, so that's basically what we have today. Now, the next release that we have planned, we're going to be allowing for third-party analysis tools to be contributed. Some of those tools will be again, in MATLAB, some of them will be in C and Java, some of them will be in things like MapReduce or Dryad or whatever. So those sorts of tools we will be granting access on cloud machines that will have essentially direct access to the data, of course protected, but direct access to the data. Okay. So such jobs, you can imagine, will be much more efficient to execute. Okay. And in the grand scheme of things, we want to use our data integration tools to allow for a federated architecture where you can interconnect to other databases from other communities, but also in many cases we'll need to have this combination of private hospital clouds connecting to the public clouds, where maybe the private hospital cloud wants to download the public data to compare against their local data, but maybe due to privacy restrictions, they can't upload their data outward, right? So we may have one-directional information flow in some cases. Okay, so right now, as of today, everything is hosted on our servers at Penn, so you can think of this as, our group's private cloud. We will continue to have this service so that users will get, some basic level of computation and data access. Our next transition, which really is being held up not for technical reasons, but for lawyer reasons, is that we want to move the hosting, or at least part of the hosting, up to Amazon. To this point, I think we've resolved the privacy issues. The actual EEG data is anonymized, and the patients have signed consent, and so on. But the University of Pennsylvania is very concerned about us signing their name to a contract with Amazon without them wrangling through all of the various details. So they promised me by the end of the month, which is in a couple of days, that they will probably have that contract ready. Okay? I don't believe them, but hopefully they will be at least not too far off. Okay. And our goal is everything we're developing is actually going to be open source software. If you want to host it on your own private cloud or even your own single machine, that will also be possible. Okay. And the end goal will be to connect up all of these. Okay. So let me just give you a couple of screenshots to give a flavor of what's going on. I figured I didn't have time to give an interactive demo. If anyone wants to see the thing actually running, I can do that afterward. Okay. So this is our basic search interface. This is an instance of these forms that I talked about. So here, there's a bunch of different categories for patient demographic information that we can use to look for EEG data. Ultimately, we will be extending this to have keyword search as well. Okay. Here's an example of the EEG viewer. It's a combination of JavaScript with HTML Canvas and Google Web Toolkit and a bunch of other stuff. But basically, what it gives you is the ability to, at interactive rates, scroll through the data, mark annotations, and so on. These little black lines here, this basically represents the entire timeline of the data. The black lines indicate where people have marked annotations. Okay, we also have viewers for other data types. So this is an example of a 3D model of the brain, and these colored dots are where the electrodes were placed. That data is actually being overlaid from the database metadata. Okay, so this is an example where we're actually taking the images and compositing other information as well. Okay. Additionally, we have the ability to interface with external MATLAB tools. As I said, that's currently our first experiments are sort of this loose coupling. So the interface is you go into this analysis thing, you say create a new analysis, you decide what data, so these are the particular channels that we're viewing here, which of these things do we want to make available to MATLAB. You select this, it creates an identifier, you paste it into a MATLAB program, which lets you then do a bit further selection. And the idea is there's a little kernel written by the individual lab that does the data analysis over whatever data they've selected here. Okay? So the data access under the covers is done through web services, and everything is carefully signed and time-stamped and encrypted so that it's unforgeable, and that if we ever end up with private data, for instance, the experimental results that a particular scientist is working on, this is not available to anyone who's snooping. Okay? And then we have libraries and so on that hide all the services. Okay. The other key thing is that we, by default, from the beginning, maintain data provenance. Okay? So when this MATLAB program runs over data from the server and stores its results back in the server, we're going to create what we call a data snapshot, which is sort of the unit of data collection. It'll have annotations saying exactly what program was run, when, over what data, and what annotations. So this will be the mechanism that allows us to reproduce experiments. In other work, my group has looked at actually visualizing data provenance and querying it and so on, and we're hoping to make use of that. One of the things that we think is actually sort of underappreciated is the lack of incentives for many scientists to share their proprietary data. we need some way, for instance, that people will get promoted, will get hired, and so on based on their effectiveness as data sharers, not just their effectiveness as paper publishers. So we're really interested in using data provenance to sort of build an H-index not for papers, but in fact for sharing. Okay? So that's kind of one of the things we're looking at. Okay, do I have a minute or two to just say a bit about what, oh good, I even have time. Good, so let me just say a bit about where we're going, because right now we're in year 2 of a 5-year project. We have a lot more ambitious plans to go. By the end of the year, we hope to have the sort of user-supplied code mechanisms put into place. So this is what we're calling the tool exchange. It's really, you can think of it as being analogous to the iPhone App Store, but, Apple has already sued a couple of people for using that name. We didn't think tool shared was as compelling as tool exchange, so we're calling it the tool exchange. The idea is, you'll be able to upload various analysis tools written in Java or MATLAB or C or Hadoop or whatever for, various things, whether it's seizure detection, event detection, anomaly detection, data quality, clustering, etc. And we'll put into place mechanisms for rating tools, but also some of the rating will come, in fact, from the usage of the tool, right? Remember, I said we have this data provenance. So, again, you can imagine this H-index for the tool also being used to help rate its quality. Okay? All of these things will be executed, in an isolated space. They'll have direct access to the data sort of running, in the cloud right next to it. The hope is there we'll have much higher rates of data transfer than would be possible with the web services. And we'll have the ability to do massively parallel computation if we can get people to re-architect their code. So we think there's actually a great deal of promise here in trying to sort of scale up a lot of these algorithms. Okay. What we have planned is, there will probably be some users of our site who won't have the financial resources to buy cycles. So the plan is there will be basic service, which is, it's going to run on our cluster. And, it's sort of first come, first serve. If there's no resources available, then you may have to wait a while. For those who can afford it, if you say, I need an experiment done today and I need 50 CPUs, you'll be able to pay through our site to have it run on Amazon Elastic Compute Cloud and get your results much faster. Okay, so that's kind of the model we have in mind. We've talked about, in the long run, if we want to keep this thing living past the span of the grant, then, maybe you could imagine putting a surcharge onto this that might be enough over time if we get enough users to actually keep the site going and maintained and so on. So there's actually some really interesting economic possibilities here for keeping these things sustainable even after federal funding goes away. Okay. Beyond that, we have a whole slew of features that are kind of planned. So one is, discussions and comments areas, feedback, and so on. I already mentioned keyword search, which will build upon a lot of the research done in my group. Some of that research allows us to learn from user feedback about which sources are most authoritative, so which data is of highest quality or whatever. We're going to allow for new kinds of data, new kinds of viewers and visualizations. We started with time series data, with plots and various kinds of image data. We're already talking about doing 3D models and a variety of other things. There's nothing in our architecture that's specialized to any of these data types. We can imagine going much, much further. Okay. We're also planning to incorporate a lot of the data integration technologies that we've developed. The kind of novel and we think exciting part about our Orchestra platform is that it makes it very easy to interrelate large numbers of data sources and to do sort of federated storage and processing of this data. What Orchestra allows is that if I have two databases, let's ignore all the details here except to say, okay, I have two different groups. They want to share data. It's easy enough for us to define sort of a data translator between these sites. Okay. This is actually written in a very high-level query language, which allows us to do things like if somebody defined how to go from here to here, we can actually reverse it. We can compose and so on. So if we add another source, we don't actually have to add a mapping from every source to every other source. Okay. In many cases, we can compose chains of translators we can do a variety of things to reduce the amount of translation that needs to happen. Okay? In addition to all this, we automatically track where the data originated and how it was converted. Okay, so there's provenance for where the data got copied. Okay, and we have capabilities for doing distributed computation and so on. Okay, so we think this will actually fit in very nicely to many of the goals of the project. It will allow us to combine sort of private proprietary data with publicly accessible data. Okay, so to wrap up, we think this is one step toward kind of rethinking data-centric science in the clouds. We hope models like this will become more prevalent as people start to think about evolvability and extensibility. You know, one of the key ideas, I think somebody mentioned this in one of the earlier talks, we want everyone to move their code to the data, not the data to their local site. Once you do that, it's much easier to share and collaborate, to document, to systematize, to archive, and so on and so forth. Okay? And really, this cloud platform is a really nice opportunity to do that because you can expand as you need. Okay? And I would love to hear from people about ideas, collaborations, new data domains, etc. We're looking to expand. So thank you very much for your time, and I'd love to take questions.
Thanks.